back into memory mapped I/O, talking about it in general, and then we'll finish up that lecture and go into GPIO in particular. Do we have any lingering questions about the course in general? Why you're here? Any questions? Perfect clarity by the class. Fantastic. Can somebody give me a definition of what is memory mapped I/O? A very brave person, you'd have to be very brave to answer this question. It doesn't even have to be right. Maps the memory of the input and output. Can anybody be a little bit more specific? Maybe a little more precise, yeah. Read or write data, that's true. Nothing wrong there, but that would also apply only for memory. Yeah?
Oh, to read and write data from peripherals?
Just tell me what memory mapped I/O is. Whatever your definition you want to give.
It's using memory addresses to access data in a peripheral device.
Yes. Yes. All right. So the big idea is, remember, the core has no idea about the rest of the chip architecture. It does not care. It only knows that it can load and store things. So it's kind of like a hack. It's like, look, I made this really limited interface, and now the rest of those other companies, like Samsung and Apple, said, okay, well, I have to use this horrible architecture that doesn't have any specific commands to do anything, and I'm going to hijack the load and stores to allow us to actually put data in a peripheral or on a GPIO pin or change or configure an analog to digital converter, right? So the core only knows about loads and stores. We're just going to reuse that architecture or those instructions to do all these other things. And so those other things are writing ones and zeros to GPIO pins, for instance. How do we feel about that? What questions do people have? I'll probably now ask that question on the midterm. Free form, what is memory mapped I/O? I'm excited to see what the answers are. Okay. We went through this example in class. I believe we went through this example. Oh, no, we didn't quite get to this one. Our friend over here, somewhere over here, wasted our time. Not wasted our time. Stalled for 1 whole minute so we wouldn't get to it. Very, very good. So this one was, how would you do all reads and all writes? What would be the configuration? Okay, for context, this is inside the peripheral, right? The whole point was that we were in the core. The core wants to do loads and stores, but the core isn't attached to the peripheral. It's not attached to all peripherals at once. You need some intermediary, and that was the APB bus. And so the bus structure is going to have these control signals, and now we're trying to figure out how do we hook up these control signals to our peripheral to do anything. In this particular example, if you want to do all writes and all reads, you would say there's a peripheral. Let's say that's the only thing on, the only address on this peripheral is, so when you do write enable, p select, and write, that means you're trying to write into it, so you're going to AND all those in. We don't care about the address in this particular example just because we're going to pre-state that this peripheral only has one address in it, which would be a rare case. We're going to take the write data bus and put it into the D flip-flop. And then the read data bus is going to come out. So now when you store a word in, you're going to be able to put at this address. Why if this address doesn't care, if we don't care about this address, how does this thing know to respond? What is the signal that will occur? Was that?
Rising edge of clock.
Well, it's rising edge of clock will always do things, but why will this peripheral respond if we're not even masking for the address? How will it know? P select, yes. So the bus initiator will go through and determine that for a particular address, an address range or a particular address individually belongs to a particular peripheral, and it will tell that peripheral that it's your turn to respond by using a p select. And we'll see this idea of a select line coming up when we talk about external serial buses. Yes?
So in the case that we have multiple buses, p enable and p write are going to be turned high and low for all of them at the same time.
Yes. If we go back to the diagram, we'll see that those lines are shared by all the peripherals.
Why not just make p select and then get rid of P enable?
Because for this particular architecture, so it's not like you couldn't make that. It's not like there's an inherent reason of physics why we couldn't do that. The architects decided that they want to make sure that P enable is done so we instantiate the data, is on the bus and stable, and then next clock cycle, P enable goes high for telling the peripheral to respond. So yeah, we could figure out maybe in a more advanced bus structure that you'll enable while the data is there and you just know the next clock cycle it should do it. Here they're just trying to put a guard in. Okay? And you could also stall for some other reason. Maybe there's other reasons why you want to instantiate the data, and then the thing has another task, the initiator has another task, it's something over here, and then it enables. Yeah.
So it's just additional redundancy to make sure that the data is stable.
Correct. That's one way to interpret this. It's not, again, we can make bus structures all the way we want, different ones. This is how this one's done. Yeah.
Just to make sure, P select is just a way to representing that this device is selected. It's not like a mux, right? Like there's multiple. Like it's not. It's a single bit, right?
It is a single bit. A single wire goes from the initiator to every peripheral. Right? Sorry, every individual peripheral. So if you have 10 peripherals, there's 10 P select lines.
Oh, okay.
Let's see if we go back. Nope. Come on. I know it's not the best diagram. You can look at the manual. Their diagrams are of this quality, so you're not, no good diagrams here, I think. But here we're just showing that every of the P select up to, gets its own line. Right? So yeah, you've increased the number of lines, but it's not that many. It's not that big a deal for being on chip. When we go off chip, you're going to find out that having extra data lines is actually a big problem. We'll talk about why that is. Okay, good questions? Any other questions? Yep.
Is there a limit on how many target peripherals you can have per initiator?
I guess in theory, no. I bet the spec is going to tell you that there's only so many peripherals allowed by the architecture they've chosen. It's probably like 32, something like that, I don't know. So inherently, no, but practically, yes. Okay. Yep. We did all that. That's multiple addresses. That's how you would mask for multiple addresses inside one peripheral. And then we talked about measure stability. Fantastic. Okay. Let's see what else we got. All right, so all the data goes back. There's data in, there's data out. So now we can load and store data into this thing. Remember that the data going back, P write data bus, there's one data bus for every peripheral. And that's nice because it allows peripherals of different speeds, of different time constraints to set up the data whenever they want, and then they'll pull P ready high when that data is ready. So now we don't have different peripherals fighting for the bus. Does that make sense? Okay. P ready, in this particular case, P ready will be ready on the next clock cycle, so we could just pull it high. I'm sure the hardware engineers will yell at you for this. When you go to your job at Cisco and start designing your own bus peripheral, don't just tie it to 0. They probably have, or VDD, they have another way. But for this class, all we can say is we don't need to add another wait state in there. We don't have to force this thing to wait. The problem hasn't asked for that. Any questions about this? Yep.
How do you know that P write and P enable P select don't have to be added to enable
How do I know it has to be ANDed? I don't want data coming from the, so there's one data bus coming from the initiator, right? I don't want, if that was enabled all the time, that means any data that was going on that bus would be latched into this D flip-flop. And I only want that to occur when it's supposed to. In this case, it's when pselect has selected this peripheral. That's the only time that should happen. And it shouldn't enable, if it's a read command, it shouldn't update this. Right, so read and write both, so read would have to be high, or write would have to be high for that to update. and you'd also have to enable. Yeah.
So for this example, to read and write it's only depending on P select and not the address. The address is just ignored in this case.
Correct. The part that your instructor obfuscated away and confused you was that should have had an asterisk somewhere. This is the only address on this peripheral. So if that's the case, there's nothing to mask for. Now, if you had multiple addresses, like a few slides beforehand, then you'd have to have some way to mask and select what should happen for different addresses. Okay. We'll talk a little bit about wait states here. So there is this idea that you can either whether it's P-ready or P-enable, it's not a requirement that they happen that cycle or the next cycle. Right? It can happen at a different time frame. So if you're writing data in, you can have different wait states. So even though this, here's the setup phase, and P-enable does not go high until here, who knows what was happening here? I don't know. But the protocol allows this to happen. Right? So you could be, why would it happen? I don't know. The initiator's busy doing something else. I don't know. But basically it's saying you're not supposed to respond until I've told you it's time to respond. Okay. And the same for the read condition. This is more consistent in what happens. Here, we're just demonstrating that the peripheral is saying it is not ready. Normally, we're tying that to VDD. It's ready immediately in some of those applications, but maybe it takes some time for the peripheral to do a task. That's the normal case. The peripheral needs to calculate the fourth digit of pi. The peripheral is a timer. The peripheral is all these sort of things. It may take more than one clock cycle for the data that is going to send back to be ready. So it's very common that you'll have lots of wait states in here because the peripheral is doing something. Also, you'll find that the peripheral clock and the advanced peripheral bus, the advanced high performance bus and the advanced peripheral bus all have different clocks or can be clocked with different clock sources. So now, actually, I guess this is a good reason why you'd have this. This is just another synchronization method if you have two different clock schedules. So having this enable go is a way to synchronize between two different clock domains. Does that make sense? Does people know what I mean by clock domains? Most people are not making eye contact. I assume that means you have no idea what I'm talking about. Just imagine if you have two digital communication things that are trying to talk to each other and they're on different clocks. And they're not a nice integer of each other. They're not synchronized. So one's going at 1 hertz and one's going at 1/3 of a hertz. You don't know when you clock in that data if it's going to be perfectly aligned on the clock edge. And so here you can use this thing to say, I've guaranteed that there's a clock edge between here. Now you can go and read the data out. So it's also a kind of a synchronization mechanism. Okay, what questions do you have? Yep.
Why enable after V2 and not after T?
Why is enable here after? Why is it there instead of here?
Instead of after. Data is after.
Data's over here?
Yeah.
Because the peripheral, so you're saying, why isn't the data here?
Or enable after.
So the initiator went through and said, okay, here's the address I want to get data out of. I want to read it out of it and instantiate everything. It's doing its job. And then it says, I'm going to enable that peripheral next cycle, okay? So initiator's doing everything normal. The peripheral decided, I'm not ready yet, for whatever reason. I don't know why. And it needed 2 cycles before it had that data was ready. So now it's instantiated the data and pulled high the next clock cycle. The initiator's able to pull that data out. So why, I don't know, but does the diagram make sense? Okay. Okay. For those people who really enjoy, I remember you really enjoyed a good state diagram. All right, so here's the state diagram for what that bus transaction looks like. And basically you see that there's an idle setup and an access state. Basically it's just giving you that one extra cycle to instantiate the data. So you can work yourself through that block diagram or the state diagram to kind of see another way to see how the timing goes through the bus transactions. There are a few things you'll that we left out because they're important but not relevant for the class, not important for you to understanding the high level. There's things like bus errors and memory address errors, all sorts of things. You don't have to worry about those. You can look through the data sheet and see all the signals that we put through there. A few of them are just not addressed. You don't have to worry about them. You only have to really worry about the signals that we talk about in lecture and slides. And again, if what I'm saying isn't making sense or you need another reference, this manual is up on the webpage. It's really not that long. A little searching through. If you just read through the, scan through it one time, you'll find out where all the data is. You'll answer most of your questions. And you obviously, of course, can post on Piazza or come to office hours as well. All right. I wanted to go, so the next lecture here, just to wrap up from yesterday, we're just going to go through specific examples for GPIO. So we talked about it in the abstract. We're going to talk about how you're going to use it for GPIO and how this kind of relates to your lab, or at least what the stuff you've been learning in your labs. Okay? Any questions, concerns? Okay. All right, so this is going to be a little bit of review of lecture 1. If you remember, the first time I showed you a bunch of pictures on, and we walked the diagram, and I showed you what the inside of a GPIO pin, and all of your eyes is glazed right over, and you didn't understand any of it. I think now you're really going to have a good opportunity to learn this. So remember, we looked at this diagram. We got the core. The core is going to be sending data, loads and stores, to make them through this highway system to the peripherals. In particular, we're going to look at GPIO. Great. Yes. Yes. Okay. Just to be super clear about this, this is all things that happen in silicon, right? All those elements are actually in the chip when you want to get data out. These are called bond pads. They're literally a pad of copper usually that's deposited on here that we're going to attach bond wires to. These are usually gold bond wires, and they take you from the chip to the pins. So there's a direct connection to the chip. These pins, this package, the black thing is called a package. The industry has made, a couple thousand different types of packages. They're all very standard. You can get them from different suppliers. And so a company like Cypress will go make their own variant as the STM32, of an ARM chip, put it in this package, and then they'll have that bond wired, and they'll epoxy everything into this black UV protectant material. Does anybody know why it's UV protectant? Exactly. You shoot it. You just take you take it outside, and you'll change the bits. Sometimes it's a bright flashlight you can put on top of your chip. It had to be pretty bright, and you start changing bits. All right, all sorts of interesting ways to attack chips from the security point of view. That's just another view of what it looks like. So I think they use, I don't know, sulfuric acid or some interesting acid to eat this away. For you guys, right, there's a wire, obviously not exactly where that trace is, but there's a trace that's copper wire that's going to take it from those pads to one of those GPIO pins, and that's what you're going to be measuring in lab. All right, so a simplified version of what this is, you have a D flip-flop for a pin, okay? This is going to come, it's going to come because of your particular kit. How STM made this particular microcontroller is that GPIO pins are on the high performance bus. Let's ignore that point for a little while. We're just going to assume it acts just like the advanced peripheral bus, because in reality it really does, although I didn't want to teach you all the intricacies of pipelining a bus. It would be horrible. So we're just going to assume that the high performance bus works the same as the peripheral bus. So data is going to come in here. You're going to store a bit into here, and that's going to be represented on the pin. Normally, this is a concatenation of multiple bits, or a register that contains multiple bits, okay? And then it's going to drive that data out on the output pin. Likewise, when you have your pins configured as inputs, so you want to put a logical 1 or 0 in, it really is, yes, there's some extra circuitry in there, but it really is just a D flip-flop, and when the clock goes, you're going to clock that pin in and hold it in there, okay? Yes, I flipped those. Off to the high-performance bus. All right, so if we look through the anatomy here, you have, so here's your output register. Data's coming in. You have some control register. Remember, you get to configure your output pins. So it's either can be an output, it can be input, it can be high impedance, it can be open collector, open drain. And then you have a control register. So all three of these registers here are to control this pin. There's also other registers that you can use, speed registers and alternative function registers to control this GPIO pin. This particularly, we call this a push-pull pair. This is, I mean, of course, there's NMOS and PMOS output stages and all this other digital logic that we're not showing. The reason we're showing it specific like this is trying to give you the idea that these are beefy. These are able to drive more current than the little circuits in here. The circuits in here are pushing out, microamps. Right? They're not really trying to push that much current just because they're designed to be fast and low power. These stages can push out much more current, which means they can actually turn on an LED or something. Does anybody know what the drive strength approximately would be for a GPIO pin? Take a guess. Yeah.
3.3.
Yes, that's the voltage. How about the current? You're exactly right, because that's the power supply for this chip. What about, how much current can this thing push out?
1 milliamp.
Any other, that's a good guess. Any other guesses, higher or lower?
Milliamps.
10 milliamps. 20 milliamps. 20 milliamps is actually the right answer, if I remember from the data sheet. But it's in the milliamps range. It's not in the amps range. You're not driving a motor off of this. It's good. And it's not microamps either, so you can actually do some work with it. But that's why these exist, right? I think 20 milliamps is actually for the entire port. Maybe a pin is individually less, but whatever it is, these can drive some amount of current. And remember that these are just, yes?
Why would we try to, how would we ask for more current? Like, we burn out the pen?
Oh, yeah. Typically, these things are pretty robust. The microcontroller manufacturer figured out that those designers do it, especially users, do whatever they want with these things. And so some of them can withstand a fault, right? So you connect it to ground, it'll survive. There's no guarantee of that, I suppose. So what would happen is the voltage would just droop in that case. It is current limited. It cannot drive more than 20 milliamps through the air. So voltage starts sagging when that happens. Yep.
Will the pin always output signals to the AHP because there's control output?
Will the pin always output signals to the, what does that mean?
To the first part.
The input.
Yeah. Will it always output to the AHP?
Yeah, it's the input register. The input register is always there. Now, the high performance bus or the peripheral bus doesn't always have to ask for that data. It's just saying, hey, that data is here. It's available. And now I suppose we could think about this existing in a larger peripheral, right? And that peripheral is controlling what data goes out based on what registers are asked for and all those sorts of things. So I guess in this case, it's not that every pin will go back to a peripheral. We'll see an example of that later, of how you have to handle that. But yes. Okay, anyways.
Is it current limited because of the load resistor that's on it, besides the trace, or is there a current sense IC on it?
This device cannot, this MOSFET cannot deliver more current. It's just not possible. It's not sized large enough to deliver more current. So it will saturate, and then that's as much as it's going to give. These things have physical size associated with them to be able to drive that much current, and that physical size is cost. And so they could give you an amp out, but then it probably has to sacrifice something else, and that would have to be a special IC that you'd want to do that for. I like the analog question. That's fantastic. Because when you get to those projects, you know what's going to happen in those projects? You're going to have to control some weird motor, and it's all going to be a disaster, and then you're going to remember, oh my gosh, I can only drive 20 milliamp motors. Fantastic. All right. These registers are all concatenated together, yes. And just reminding you that the structure, we call it memory. We call it memory mapped I/O. You could call it register mapped I/O. But we also have the term register is very specific for the core, because the core has the 16 registers that the processor used. That's a different connotation of the word register than we're using the peripherals. These are D flip-flops in the peripheral. Do you have a question? Okay. Yep. Right. And exactly, you're just going to use store commands to put data in, load commands to get data out. Okay. So it's important to think that here, these things are concatenated together. So yes, every GPIO pin has this data structure, or this hardware structure behind it, but it's all concatenated together to make a port. So your port may have 8 bits or so on it, depends on what your configuration is. And it's not going to be like a random individual D flip-flop hanging over here. They're going to go and group those all together to make a register from a layout point of view. All right. So here in this example, you can imagine that you have addresses assigned to registers, and then when you do your stores and loads, here's that address, and your peripheral has to decide when P-select goes high, it's this entire port, the entire GPIO peripheral, and then it has to decide, oh, this address range is associated with that particular input or output or control pin, and then you're going to be pushing that data into here. So back to your question, there would have to be some sort of muxing structure, actually not here because they're all inputs, but all those peripheral outputs with all the other things in there, there'd have to be some muxing structure because you can't have node contention. You can't have multiple devices trying to write to the same line on the GPIO, on the high performance bus. All right. Yep. Everything we're talking about exists in the peripherals. And then because one of the challenges you might be having is that we keep using this word register. And there's 2 connotations of register. There's one in the core, and then there's one register or memory location or I don't know, whatever you want to call it, and that I call it register, that exists in the peripheral as well, because it really is just a bunch of D flip-flops. Does that answer your question? Okay, good question. All right. I think I'm beating the horse to death, but that's fine. It's an important concept. All right, so port mapped I/O. This is the kind of Intel x86 class AMD processor style where you're going to make special instructions that will do a task. So you want to talk to memory. There's a whole set of sub-instructions in that ISA just to talk to memory. But that's not how it works in ARM Cortex architectures or most microcontroller architectures because they're called load stores. That's the only way they are able to interact with the world outside the core is through these load stores. And so we call that memory mapped I/O, where there's a memory allocation or an address that's associated with the I/O or peripherals or whatever, anything that happens outside of the core. So simpler, more convenient. Yeah. Yes.
Is there a concept of like a virtual address memory mapped I/O? Like, can I have 2 addresses mapped to the same physical register, or is it generally going to be one-to-one address maps to one register?
Address is one-to-one.
There's no like virtual addresses.
No, we're not complicated enough for that stuff. There's no like applications. There's no, right? You might have multiple threads. That's about as far as you go into the OSy kind of world. But there's no, you don't have to worry about. I did use the word virtual address in one slide. It's not virtual addresses from 370. It's a different kind. We're reusing the words. English language is not precise, but it's very expressive. That was just the idea that you could have a state machine that represents a group of addresses, but there is no actual register there. It's just a state machine that says, you talk to me, I will act like I'm that address, and then do something on that. Okay. Okay. So just a reminder that this is the memory stack. When we are using loads and stores, this is, the core makes no difference between any one of these addresses. These are just places to store data or read data from. It's up to you as the programmers to know that that register or that memory location you're putting data has this other meaning. That other meaning could be configure the register or configure the I/O port, right? It's up to you to be responsible for that, not up to the core. Yep, okay. All right, so let's dive into what the actual register looks like. So this is straight from your manual. And it's not, I know it looks scary, but all the pieces you should more or less be able to figure out now. There's GPIO output register, GPIO input register, there's a configure register over there, and then there's data lines to control the state of the outputs. Remember, I guess I drew it a little bit wrong before. Here, the control can even make this thing not connected no matter what. It's not either going to be a 1 or a 0. It could be high impedance. You could turn, that could go high, this could go low, and then this would essentially be isolated. That allows you to have this become an input. Here's other features here. Does anybody know why these diodes are put there? Ah, damn, it says it. You guys are so smart. Oh my gosh, yeah, very good. These protection diodes are put in there so that if you accidentally put like a 5-volt battery on this thing, it won't destroy the device. What will happen is current will come in here, it will flow up through that diode into the VDD pin and start trying to raise the voltage of the entire the entire PCB. And usually something else will stop it, like, it's not guaranteed, but it's a way to protect the chip by sacrificing the rest of the PCB, let's say. There's also, they can't get away from this. This is just almost inherent to the architecture of NMOS, and these exist, and so they just accentuate them by putting over voltage protection and under voltage protection. They're also part of ESD protection, so you should always just be, especially in the winter, be somewhat careful with ESD, touch something metal before you're playing with your dev kits, but if by chance you don't, there's a good chance that this would protect you from a kilovolt but low amperage over voltage situation. Your GPIOs also have the options to enable internal, yep.
What does ESD stand for?
These are great questions.
Yeah.
Turns out you haven't been doing this for years. Okay, ESD is electrostatic discharge. So just static electricity. Any other good questions? Yeah.
So the protection diodes just are there to stop you from sending in too much voltage to the chip?
Yeah, they're over voltage. They're ESD. They're really good for ESD protection, but yes, they're. If you put in, what if you put in -5 volts in here, right? Then that's still going to go this way, right? You're still going to protect from under voltage protection situations and over voltage situations. Now it's not going to be like you can still destroy the chip. Like it's not hard to do. It's just trying a little bit to help you. Yeah, there's actually an interesting error condition I had on a project where I was harvesting some energy. I had one 5-volt or some variable rail that could go from like 1.8 to 5 volts. It did whatever it wanted to do. And then I had 1.8 volts for a low microcontroller. And sometimes I had a condition where the clock started going crazy. The clock would just be some other speed I'd never thought about. Like, why is the clock going fast? What's happening is at certain points, the voltage on that I/O pin would be 0.3 volts over the VDD of my device, which means it would start conducting current. And then it would start raising the voltage. It would, overpower the regulator and start raising the voltage of my entire PCB. Fine. The parts were tolerant. They could go up to like 2.5 volts. So that was okay. But then the ring oscillator I had started going faster, and I couldn't figure out why all my timing was wrong. But that was, as a side note, I thought that was fun. Okay. You have pull-up, pull-down resistors. These are actual physical resistors inside your chip, which is kind of a cool option. And you can optionally enable them. And so that means that you could have a pull-up resistor. So if you have a button or something, you could have that be pulled up without actually having extra hardware on your device. Yeah.
Does that mean that I cannot have an analog device, device that create analog signals attached to the pin?
Why not?
Pull up, pull down.
These are optional. You can. They're on switches, so you can. I know it does not shown here in any clear way. Somehow that's supposed to be a variable signal, and there's a line going in, so you can optionally enable or disable these resistors. Why would they do this? Why would they spend, there's area inside the chip. Resistors are actually far larger than digital MOSFETs and logic gates. Why would the manufacturer spend all the money to put resistors on every GPIO pin? Sure, but we could just tell the manufacturers, put your own resistors on there. Why are they putting them in silicon?
preventing short circuit.
You could maybe. The market has gotten to such a state where manufacturers like STM are trying to woo customers away from all the other ARM manufacturer or ARM chip manufacturers. And so they're saying, we'll give you extra features. We're going to allow you to have slightly smaller PCBs footprints because those two little tiny resistors that you would have had to have outside, we're going to put them inside now, right? And the little extra cost, literally less than a cent for a resistor, we'll save you that by buying our chip, and we'll just have them internal. So that's the state of the market now. You can actually buy your microcontroller or STMs that you have now have op amps built into them that you can optionally configure to turn on. And so you can put an amplifier in your circuit, route signals in, amplify them, and send them back out and go into the ADC because they know the market's going to need them. So you might as well buy our chip. We already have it for you. Just kind of a cool fact of how mature this space is now. Okay, talking a lot. Maybe I'll get through this. Let's see. So now we have, these are optionally, you can put these on. This is really going to be really useful when you talk about I2C buses which require a resistor. Yes?
What is pull up and pull down?
It's fine. We did have a homework assignment on that, or maybe talked about it in the first class. It's this idea that, how do I describe it? Okay, so I have a resistor to VDD, like up here, okay? And that will pull current up and raise this line. If that was the only thing on that, raise the line up to VDD. That makes no sense, does it? I'll give you an example. We'll look at false sod together after class. Okay.
Full signal high, pull down signal low.
Yes. Sorry, just listen to him. He knows what he's doing.
So is it just driving the voltage up to like, it's going to do pull up and drives voltage upwards?
Yep. So you could have, say you had a button here, right? A button, and you didn't want to, and if they just have a button and connect it to VDD, here's VDD, and I just put a button here, and let's see, where do I put the line? I put the line here, this goes to my microcontroller, right? Like that. No matter how much I push this, I'm going to push this, it's going to be high, and if I push this down, I'm going to short out my, my battery, basically. I'm going to make a short to ground, and something's going to fry. So you don't want to have that. So another way to do this is you go put a pull-up resistor up here, and this is a switch. And so this thing is gently pulled up high. So if this switch is open, say this is 100K, then this will pull current up, and drive this node will be VDD. Until you press this, then this will be pulled down to ground without blowing anything up. That's why you use them. There's lots of other ways to use them. They're useful enough. All right. Well, anybody is excited about analog, we can talk after class. The last thing I wanted to point out is that there's a Schmidt trigger. Schmidt trigger, I think I have a slide on it later, is a nice way to control is if you have a signal that bounces a lot, this will take care of that. And then there's also ways that you can route, if there's a mux there, you can route your analog signal to, say, an ADC or somewhere else with your configuration register, or you can pass it through the Schmidt trigger, which turns it into a clean digital signal, and you put it into your GPIO. Okay. Yes, and each one of those little registers is made of D flip-flops. I basically went through all this in detail, forgetting that I put it in slides. Let's see what I forgot. Data inputs, you can have alternate, these alternate functionalities. You'll find sometimes you can have a DAC, so your digital analog converter, or you can have a SPI bus or some other functionality you can route through your GPIO pin. So there's a register that allows you to control that as well. So that would be your configuration register. You'll see that under alternate functions. We talked about that. Yep. Basically, I did the whole lecture just on one slide. All right. So here's an example of your clock registers. So these are another set of registers that are in this peripheral. they all have addresses associated with them. So this is another case where you have multiple addresses for a peripheral, so you're going to use a p-select to tell this whole peripheral to pay attention, and then the peripheral itself will figure out which address, by masking, which address you're actually talking to. And so this is an example of you can actually change the clock, which clock is going to things, and how fast that clock is. You can look at the mode. In this particular case, you have 32 pins, or 32 bits registers, but there's only 16 pins in this example. That's because you have 2 bits that represent the mode. So why I'm bringing this up is that you're trying to figure out how do I configure this register? And basically, you're going to go look through the data sheet for this exact thing, and then you have to go interpret, okay, we're talking about mode. The mode register for pin 2 has 2 bits. What do those 2 bits do? You have to look through this thing. I have to go and select. I want this to be a general purpose output mode. So now I have to store, store and mask in just the bits I want for that location. So that's a lot of the task. When you don't have cube ID, kind of masks a lot of stuff away from you. But if you really want to look into the data sheet and understand where do bits go, you'd have to do a process like this. You see what the bit mapping is, and figure out what bits you have to put in there to control your registers. Yeah.
What is that UL
UL.
You have 3 UL and 1.
I'm trying to remember. I don't know. I'll go look it up. I forget. Is it unsigned long? It doesn't make sense in that context, but maybe. All right, that's a good question. Ask on Piazza. I will go dig into it. It's been a while since I made these slides. We talked about the output type register. Again, it's a register. This is the physical. This is a visual representation of that register. It's a 32-bit register, but they don't care about the top bits, right? These are reserved, meaning they're probably not even there. Right? The manufacturer isn't either. Just saying, okay, maybe in the next microcontroller rev or something, we have more pins, then I'd put that back in. So here's an example of you want to go and set this to an output pull-up, output to be a pull-up state. Then you go and set that pin there. Yeah. Yeah.
For the previous slide, what exactly are all pins? I know we use input and output all apps, but what are the other modes?
The best answer is you got to go look it up in the data sheet. But I can tell you, alternate function mode could be something like SPI port or some other peripheral, which we'll talk about later, that has a function. The thing is that you'd have to route that function out of the chip somehow. And so they allow you to reuse a GPIO pin rather than having a pin that's specifically, here is the analog input pin. It can only ever be analog input. Well, that would be a waste of pins, and we have a limited number of pins, so they just duplicate it by having a mux that's going to switch that functionality in and out of the device. Does that answer your question?
And the analog mode, just what again?
So say you want to pass an analog signal through a pin, right? So you might want to send an analog signal to an ADC. It's just going to pass it through that pin. Yeah.
So, in the next slide, if we were to word to those reserved bits,
Yep.
does anything happen? Do you have to worry about that?
Nope, it's fine. This is going to ignore it. And you write a full word in there. Those registers, if they exist, will not change, and they don't exist.
And they don't.
Yep. And you can try and read something out of them. Usually, is default, it'll read 0. But I think the manufacturer is going to say we don't guarantee what that data is, and you're responsible if you get noise out.
With the lower 16, it's still be changed.
Yep.
What's the difference between output push-pull and output?
Push-pull is you're going to be able to define 1 or 0. Open drain is you're not controlling the PMOS, you're only going to control the NMOS. So you can pull current in or your high impedance. And that will become important in like 3 or 4 weeks. In fact, there's a slide, fantastic. Push-pull. kind of the classic. You can either push current in or pull current out. And then open drain is you have the option of pulling current out of that pin or leaving it high impedance. And high impedance means disconnected. High impedance is like high resistance. So a mega ohm would be high impedance. All right. Let's see, given the time, I want to get to example. Basically, these slides are fantastic slides I didn't get to. They're some of the best slides. They're just pointing out that, look, there's different GPIO configurations. This is GPIO speed. Why would you care about the slew rate of your signal and being able to control that? Why not just go fast all the time? Why would we want to go slow? Yeah, okay. But this is like the rising edge. How fast is that transition from 0 to 1? How fast does it transition up? Why might we want to go slower or faster?
It's like interfacing with it. Right. Oh, I guess this is output.
Oh, yeah. I like where you were thinking. To go fast takes more power. You have to push more current through. So now you're taking a power penalty by going fast. Also, not demonstrated here, things that are fast often ring and create extra noise that you have to deal with. So generally just go with the default until you have to go fast. Don't just choose fast. It's not always going to be better. There's penalties for fast. Fantastic. What was I going to tell? Oh, here's the output register. You're going to actually set the output to be 1 or 0. Fantastic. All right. We'll talk about the input chain a little bit. We already went through this. We have pull up, pull down resistors that are optional, over voltage protection or ESD protection, Schmitt trigger. The Schmitt trigger is actually a pretty important thing, a little bit overlooked. Here's another example of having pull up and pull down. So here's a resistor this attached to the pin, and this will naturally raise that pin up to VDD unless something pulls it back down. That will naturally pull it down to 0. There's times when this is useful. Sometimes you just also want to reset a pin. Say you have some analog device out there and you just want to drive it 0 in the very beginning. You could use that method to do it. However, it's important, what I want to get to is signals are often time varying and noisy. If you actually get your oscilloscope out and look at your digital signals, they don't always look like nice square waves, especially when you zoom in or go fast. And so oftentimes you can have situations where you have multiple transitions and you didn't mean to, especially maybe you're just trying to go from here, you're trying to go from low to high, but there's a little loop in between, a little down, and now you've gotten a high, low, high, and that's not what you intended, but there's noise on those things. And so one way around this is this thing called the Schmitt trigger. Basically, it has hysteresis, has a little bit of memory. Hysteresis giving you this idea that there's history involved. And basically it says, if you're going to transition from low to high, you have to go pretty far high before we count it. It's not like we're just going to go 50% and allow you to wiggle. You have to go very high before we count it. And then when you're returning, you have to go very low before we count it. So there's kind of this window involved. And that allows you to clean up signals. So that's just an example here. This is literally a trace for, I think it's an I2C bus. And look at, this is what is called bouncing. Your signal is bouncing around. This is a very common thing to see. And you wouldn't want to be catching, this is supposed to be a low here. You don't want to be catching this as a high, low, high, low. So Schmitt trigger is a way to clean up your signals. Yep.
And it's like the same way I talked about what logic is there in the logical one. There's like that unknown.
Yes.
We don't want.
So we talked about that metastability is where your clock edge would happen like right here. That would be a challenge as well. And so the Schmitt trigger helps with that a little bit. Yeah.
So simply like increase the threshold of determining this a high signal or not.
Yes, and it's an asymmetric threshold. So going forward, it has to be higher than 50%. In reverse, it has to be lower than 50%. That allows your signal. So you can go, you're low, it's low, 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 now it's high. So you can wander around in this space without it being flipped between 1 and 0. It has to go all the way up here, stay up here, and then come back down. Okay. Yeah, and so this is just an example of all the circuitry is inside your GPIO, which is part of your larger circuit. Okay, between this and your lab, you should be comfortable kind of rooting around in here and getting a problem and say, like, how do I go and set this to be in an output mode, right? Where is the register for the output mode? It's not in the core, it's over here in this peripheral, and then it has certain connotations about what it's going to change. And then as you expand further on, we're going to talk about other peripherals, timers, we're going to talk about serial communication, analog digital converters, and these other things. They're all just an extension of this. They're all registers out in this peripheral space, whether it's the ADCs or the PWMs or the UARTs. It's just registers, and then they have some other functionalities. The registers manipulate state here where they're manipulating these analog circuits or the inputs and outputs, right? That's just the big concept here, that you're going to manipulate peripherals just by acting as if they're memory. All right. Talked a little bit about extra functions. I just listed them here. Analog digital converters, PWM, op amps, etc. All right. So here I wanted to go through this example, and we have barely enough time. Guys got me talking about Schmidt triggers. Over voltage protection, too exciting. Okay. So we're just going to go through this example of here we have this base address, the GPIO A port. This has been placed in the memory, and you have a label here, which is GPIO A base is at that memory location, and then you have your offset. And that offset is in this peripheral, the output register is at 14 above that. So you could go figure out what the address is. And basically all we're saying is we're going to try to, we're going to load the GPIO port or the GPIO base address into the registers. Fantastic. Let's see, we're going to set a pin high, and then we're going to write that to a register. All right. So just as a reminder, that's happening in the core. We're going to transit through the bus structure. That bus structure looks like this. There's initiators. There's GPIO ports. That port A, for instance, is going to have multiple addresses inside of it. We're going to instantiate bus traffic. The initiator is going to use those commands to instantiate bus traffic. Okay? And this is the example, same examples we did last time. GPIO port B is never going to become ready. It's never going to be P-selected, right? But it's going to get the same address, it's going to get the same clock, it's going to get the same data. However, GPIO port A is going to get selected because it's within its memory range and it's going to be enabled. Actually, they all get enabled, sorry. But this is never going to return ready because nothing's ever going to happen here. It was never selected. All right, so that's the setup. What I want you to do is figure out how to wire this thing up. Okay? Oh my God, you'd be all right. Yeah. Oh, uh-oh. We're in and out here. So, what you're trying to wire up, yes. What am I trying to do and why am I here? Fantastic. So you know you're going to have some pins over here. What you want to be able to do is to set this GPIO pin high, low. You want to be able to configure it, right? Now you have some registers in between. You have the input, the output, and the mode. How will you need to set up this structure here? And how does it get wired so that when a load command or store command's in, this operates correctly to put ones and zeros over here? Yeah? Is P ready always high? Sure. One done. Everybody got 1 point. Okay, so let's start out. Where does clock go? Everywhere. All right, you got 2 points. 2 points. Next, go through maybe the easier ones. You could probably figure out pretty straightforward where do the data port, the P write data and P read data, where do those must go? And keep in mind that these are 32-bit registers, okay? This is an example of one GPIO pin. So when you're connecting up to this, you just have to remember this is one individual one and not 32 of them.
So do we need to put syntax saying like we want the 0?
Will write data is going to right? Yeah, there's the P write in IBR problem.
Oh, yeah.
Oh, he has the big ones on the side.
Well, your GPIO or your registers were not labeled on the sheets that you got, but you can use that mapping up there.
Should we put
Oh, yeah.
So where are we sending?
My right is
What are you thinking?
I think there's probably like
G is not right.
that's probably
There's just some small nuances in there. You've definitely got your broad strokes.
So which one did turn on? I guess we have a code.
I thought it was just a key, right? I don't know what.
Yeah. If it's low, it's right. Maybe it's the head.
I don't know why. Something is out here. I need this to be high, and I need some out here. That's not how that works. You're driving the wire easily. Stop it. Stop. That's how it's supposed to be. That's the exit. Put a diode over it. You get it wrong. You need to. It turns. It's turned. You follow the wire. Whoop, whoop, whoop. Oh, it's not even that.
That's going into GPIO in.
It has to go into 10, right?
Yeah.
You know, something like the output reliability,
By writing to the output we're using it and P-write is low for writing. So I would just want to add like a not gate on P-write. So that's now we store data or store data just supposed to be. Or we're giving ODR.
The arrow shows that UW data is input data and read data is only out of there.
PR data.
Isn't the input register always enabled?
PW data.
Yeah, yes.
Yeah.
You can read and write.
So it wouldn't need to not be, right? The anti would only be for the
Yeah.
yeah. And then went straight to the data.
Something like this, right?
Just go straight to the
So this P address goes into
But if I have the right line, this and this, I mean, that makes sense.
Yeah, you're trying to transmit to me that you understand the control of
I need to like and he also connected to the data has to go
That's correct. Or sorry. You are correcting your data.
I did it. Electrical engineering.
That's fantastic. Curse your professor for not making the worksheets correctly, and then you look up here.
Oh, okay. Got it.
You've already made up for my mistake. I'm going to invent something for you guys. Invent magical NAND gate. So you can just write on it, mass, and then you write the address, right? Whatever address you want. Or you can just say for Alright, so that's the function of that. You don't want to write and try and get bubble logic and it's too hard. Just write it in the AND gate and say it's only go high when certain event occurs.
We need the address because so many ones
This is that's a good question. This is 32 bits. This is resistors for all the registers for all the pins in them. I should have made that more clear. That's okay. You're learning.
Okay, so then I can ask. I still don't know what to do.
Well, if it's output, you might want to.
Okay, so basically the data
I don't know how to send it into my box. Control lock is control lock is control lock. I know. That's how I do my job. Some security, you know, layout designer, layout really bad, and then I can't figure out.
Part of the problem is I didn't
So it's harder to add the magic laws. Is it once you just magically get the correct bits or something?
I guess we
Like that does make sense.
Oh, yes.
This probably doesn't. That's supposed to be. I thought it was just like this is what's happening. There's the title. We're gonna see. I guess in my mind,
we could just do like a
this. It's really this. Like two ways exist. My mind is an abstraction. For example, like if you're an abstract. Oh, I agree. I think it's abstraction. This layer, this layer. I also think more like so.
Just means like the peripheral.
There's a reason to miss myself.
In this case, it's like doing something prior to that is before and be written upon. And so, yeah, it's ready, right? And so, we have some books that like the address would be the selected things, right? Oh, it's right there. Actually, yeah. I guess that's what the magic was. That's what I was. Yeah. Well, is the D on the GPIO register connected to 3, right?
we did. Is there actually like a?
Oh no, exactly.
When we were in here, right?
I think it would be right because you only want the peripheral and the concept already said like not correspondence with
Yeah, I think so. Yeah, that makes sense. Ask your question.
And then the data will just always be covered on grades. Or is there something that should, or should the label be connected to the label or something like Oh, is that what instead of being always on. Is that just music or peripheral is right? Yeah. Because like if we have it always on, then it's gonna like just like right? I don't know. I don't think that's It's like I feel like you would have drawn it on the tire, but then again, there were countless errors
All right. Let's see what I came up with, and you guys can groan and say, you didn't say that, or you didn't tell me it was 32 bits or 0 bits or whatever. But you're here to learn. We're going to go through an example. You guys can tell me what you think. Okay? All right. So I want to put data into these registers. Okay. So the part I forgot to tell you because I got lost and was in a hurry is that this is 32 bits of a port, right? Each one of these would have a different address. If you didn't get that, You thought it was all P-select, I don't care, it's fine. Still getting all your credit, don't worry. And this is just one pin, okay? So this is all the registers, that's one particular pin. And so we're going to be able to read from these different addresses, okay? So each one of them has a different address, and we're going to read data, or write data in and read data out. So what do we connect to write data into these registers? I saw your answers. You have almost everybody has it correct.
You have to put your data into GPIO in at the feed.
I think this is what you mean, right? So remember, oh, this other good question came over here. This is not from the perspective of the peripheral. These labels come from the perspective of the initiator. So it's the initiator that's writing data into the peripherals. This is not the perspective of the peripheral writing data up there. We try to give you a hint there about the nomenclature in the spec with that arrow. So here we have 32 bits going to each one of these registers. Okay. Yeah.
What about the logic for like the mode register? We have to like set the specific pin and the specific port. So how does it know which one if you're passing all 32 bits to it?
We could go look in the motor address definition, and it says which pin does what, and if you put a 1 in there, then it does this. If you put a 0 in there, it does that. So you'd have a mapping. Here we're just talking about how to wire it up. So you're right, there's a hole in this, and exactly like was this high or low, right? Is this active high or active low? We didn't really cover that. We're just trying to say we're going to connect it, and then a different part of the spec to define what the actions are. That's a fair question. All right. What about reading data out of the registers? How are we going to do that?
Just connecting the read data with the GPIO.
All right. Now I got a problem. I got a problem though. I got 3 wires. What do we do now? Because if I connect them all together, then this one's low and that one's high. It's going to burn out the chip. You need a mux. Okay. Fantastic. We put a mux there. All right, and then we'll connect that to the output. So now we'll have our address. We'll select which one of these things will be connected to the output bus. Right? So the data is always present here, whether it's enabled or not enabled. You put all zeros in here, all zeros are coming out. It's just that they're not exposed to the advanced peripheral bus until address has selected one of those muxes, essentially. All right, we already talked about clock. Clock goes everywhere. Let's see what's next. My notes are too small. Let's find out together. Oh, I remember. So we need some way to mask out the address. So these are different addresses. I didn't give you the address numbers. There's no way you were going to get the bubble logic correct for 32 bits. Nobody wants to do that. So I'm just going to fake it. I told some of you to fake it. Just right here, I make a magic AND gate that masks for this thing. That's easy, okay? I'm not going to, your ability to write ones or bubble logic is not what we're testing here, but you would need some way to connect this address and select which one of those, what should happen. Okay, so now we have masks for the address. We also have to have some AND logic for writing or enabling our registers, essentially. So here we're going to AND all those together. And technically we need this extra logic to do that. So here, if you are, and I didn't actually expect everybody to get this exactly right. I wouldn't give you this on an exam, you die. Right? the whole point is you guys gotta think through what's in here. You try it out. Right? So here we got, if you want to write to the GPIO in up there, you'd have to, or let's look at this one. This one you have to have the address be true, and it has to be right, and it has to be enabled, and it has to be selected. So this plus that has to be true to enable this register, and that's enabling the data from P-write data to come into this register and be clocked in on that next edge. Okay? How do we feel? Yeah.
Why is the AND for GPIO motor going to GPIO?
Oh, because I made mistakes? Let's see. Motor is going to, yeah, okay. All right, I'll switch those. Very good. Get an extra bonus point today on a worksheet. Doesn't count for anything.
I'm kind of confused with the bus and what's going on there.
Okay, so if I have, let's say this register happens to be all zeros. Okay, 32 bits, all zeros, and that one happens to be all ones. And I wire them together. What happens?
It doesn't know what to choose.
It's not that it doesn't know what to choose, it's you just had a fault from VDD to ground and you burned out your chip. Right? Because now the output pins here are going to try and drive that 0, and the output pins are going to try to drive for 1. Okay? So we need a hardware mechanism to overcome that. So we use the MUX. And the MUX is just going to switch which one of these yellow lines is connected to T-write data. And how you're going to do it? Well, it's whichever address you asked for is going to select through that MUX.
But why are you passing the MUX to P?
Why am I passing the MUX to P? Because we're reading out of the peripheral. These are from the perspective of the bus. These labels are perspective from the bus. It's fine. We're learning. Active learning.
Also, mode has 2 bits and 72 row. Or 72 lines, like more than you say AND logic.
That's true. If we're going to go for the full, most precise thing, but in theory here, we got a way to control this register, right? We never really defined how many bits was in here. Yes, I can see how this can be unsatisfying. Because you're like, I want it to be perfectly correct, and I was like, I want you to have the feeling of how this works, and those two things are colliding. I get that. I promise on exams will be more about the correctness, not about the feeling. All right. The output here, right? How do we load data into the GPIO in pin? That comes from here. And in this particular case, I've only drawn 1 pin. I could have done like multiple pins. It would have been crazy. And so here's the 0th pin. We'll go into there. Let's say. I think learning occurred. What other questions do we have? All right. Let's see. They're always this one's always enabled. It's always correct each clock cycle. Okay, so we'll always enable that. And this thing, the data is going to be valid within 1 clock cycle. Okay? There's nothing here that's causing an inherent delay. Yeah.
Why is that enable always high instead of having to do with P-write?
The data is always valid in there. It's always going to be updated from this pin here.
Aren't there times you don't want that data though?
You don't want.
Like if you're not trying to read, should that register be off, or does it not matter?
Well, the data doesn't go to the bus because it has to go through that MUX.
Right.
So it can just be whatever the data is on the input gets held there and is reflected in that register. That would be fine. In fact, in this particular configuration, when you output a 1 here, it's still connected there, and you'll have it represented in your GPIO input. It loops back in this particular configuration.
Why is it the 0th bit?
You could have sent any bit because I never defined which pin this was, but I just wanted to make sure you were thinking that, oh, this is just a single pin going to here. It's not a 32-bit bus going in here from this guy. It's a small little detail. Yeah.
In GPIO, have a 1-bit input, but
We're just saying, this is a fair question. We're just saying that in this particular example, this is 1 GPIO pin. Let's say it's GPIO 0. And there are 32 inputs, and we're just saying the 0th pin, yeah, is going in there. And so I could have put 32 of these symbols here and have you wire them all up, and it would have been even worse experience than what you're doing right now.
But can't you have like a 32-bit analog number from a single pin? Or is there?
An analog number, yes. But this is digital, so it's either going to be 1 or 0. And so we're just saying that it's basically like you have lots of different wires, and we're saying only this little wire is going to go into here, even though these other wires are undefined right now. All right, we'll take one more question. No, you all gave up? Okay.
For the match, the match is the line of registers.
Yeah, in this case, yeah. In the real world, you make this kind of like control logic table, custom logic table, you would use AND gates, but this is an easy way to do
Yeah, and you look at my glorious diagram. All these other people